This is a video to work out the problems on the review sheet for the test covering Chapter 4, and then there's some review, a little bit of review from Chapters 1, 2, and 3 as well. So primarily this is a Chapter 4 test. Let's get right into working out these problems. So number one, we are to simplify, and we're going to need to use our exponent properties in order to accomplish that. So the way I like to approach this is try to simplify within the parentheses as much as possible. For example, this fraction 8 over 24 would simplify to 1/3. And where I have x's, same bases here that are being divided, I use the property that says when you're dividing the same base, you subtract the exponent. So x to the 2 minus 3 power would be x to the negative 1. And then here I'm going to do the same thing, subtracting exponents. I get y to the 3 minus 2 power. That would just be y to the positive 1. And all of this is going to be raised to the 4th power. Okay, so when I raise 1 to the 4th power, I still get 1. When I raise x to the negative 1 power, I get x. Remember, when you raise a power to a power, you multiply these exponents together. So that's like saying x to the negative 4. But remember, we always change negative exponents to positive, so x to the negative 4 on top is going to go down to the bottom as x to the positive 4. Okay, and then y to the first, remember we raise this also to the 4th power, and we get y to the 4th. And down on the bottom, we still haven't raised the 3 to the 4th power. Remember, everything in the parentheses needs to be raised to the 4th power, and 3 to the 4th power is 81. So writing this a little bit neater, now that I've kind of stepped through raising all of the variables and numbers to the 4th power, my final answer is going to be 1 y to the 4th, or just y to the 4th, over 81 x to the 4th. Okay, so just trying to make sure you understand your exponent properties here. All right, same thing here, similar problem. We can approach this really 2 or 3 different ways. I think I'm going to go ahead and do something similar. I'm going to go ahead and simplify within the parentheses first, and that means I'm going to do a to the negative 7 minus 1 power. A to the negative 7 minus 1 is a to the negative 8. And then when I do the b's, I'm going to do b to the 2nd minus b to the 6th. And 2 minus negative 6 is the same thing as saying b to the 8th. 2 minus negative 6 is really adding. So that's b to the 8th. All right, and now we're ready to simplify. I'm going to raise all of this to the negative 3rd power. Okay, so everything, all of these factors get raised to the negative 3rd. 5 to the negative 3rd. When I raise 8 to the negative 8th to the negative 3rd, remember I multiply exponents here, and negative 8 times negative 3 makes a to the positive 24. When I raise b to the 8th to the negative 3rd, same thing. I multiply 8 times negative 3, and I get negative 24. Well, again, I'll just show it like this, but b to the negative 4 in the numerator needs to be changed. When I make it b to the positive 24, I put it down in the denominator. And now I need to change this 5 to the negative 3 power. Well, remember, 5 to the negative 3 is the same thing as 1 over 5. Remember what negative exponents do. We write the reciprocal of the base, and then we change the exponent to positive. So 5 to the negative 3 is really 1 over 5 to the positive 3, which is 1 over 125. All right, so my final answer here, I'll just clean this up, is a to the 24th over 125b to the 24th. Okay, moving right along. Got one more problem in this section, and we're supposed to simplify this expression. Remember, before you multiply, according to PEMDAS, you always do exponents before you do multiplication. So I need to raise this product a times b to the negative 2 power before I multiply times this other monomial on the left. So a squared b cubed, just going to write that down, and that's going to be multiplied by a to the negative 2 times b to the negative 2. Now you could do this a couple of different ways. I'm just going to go ahead and leave it like this and do the multiplication, remembering that when I multiply like bases, I add the exponents of those like bases. So a times a, I'm going to do 2 plus negative 2. A to the second times a to the negative 2, I'll just write it out like this. It'd be like saying a to the 2 plus negative 2 power, which means a to the 0 power, and anything to the 0 power is just 1. Okay? So I got 1 from multiplying these a terms together. Now let's do the b's. Same property. I'm multiplying, the bases are the same, so I add their exponents together. It's like b to the 3 plus negative 2 power. And 3 plus negative 2 is 1, and that just makes b to the first. So the final answer here, don't really need the 1 times. The final answer is just b to the first, or just b. Okay. All right. In number 4, I told you to expand this binomial, m minus 1 raised to the 4th power, and I said you could choose either method. So I'm going to go ahead and show you both methods so you can pick which one you like the best. Let's start with the triangle, Pascal's triangle. Remember how to make that. We start with a single one, then we have 2 ones, and then we follow a pattern. Each row begins and ends with 1, and then we fill in the middle by adding the 2 numbers above. So 1 plus 1 is 2. And then the next row would be 1, 3, 3, 1. Next row would be 1, 4, 6, 4, 1. Well, remember, when you expand a binomial, your result should be one more term than what the exponent shows. So for exponent 4, I should show 5 terms total in my answer. So I'm going to go to the row of the triangle that has 5 numbers, because each one of these numbers represents a coefficient for one of the terms. 5 numbers, 5 coefficients, 5 terms. Okay, so here is expanding using Pascal's triangle. We take a number from the triangle, multiply, now we look inside, and we take this first term and raise it to whatever this exponent outside is to the 4th power, and then the number inside, negative 1, starts off at the 0 power. Okay, next number from the triangle. This time we're going to go back and we're going to raise m to the 3rd. So m is going to decrease by 1 with its exponent as we go through. Negative 1 is going to increase by 1. So the first term's exponent is going to go down. The second term exponent is going to go up. All right, next number from the triangle, 6. M goes down. Negative 1 goes up. Next number from the triangle is 4. M goes down. Negative 1 goes up. And then finally, the last number from the triangle, m is all the way down to 0. Negative 1 goes up to the 4th. Okay, so I wrote it out like that just so you could see how the pattern works. And now let's clean this up for a more simplified answer. So this says 1 times m to the 4th times 1. Remember, anything to the 0 power is 1. So my first term is going to be m to the 4th. Here I'm going to do 4 times 1 times negative 1. That's negative 4 m to the third. All right, here I'm going to do negative 1 squared. Remember, always do exponents first. Negative 1 squared makes positive 1. Positive 1 times 6 is positive 6 m squared. Okay, we're on the fourth term. Exponent first. Negative 1 to the third power is negative 1. And negative 1 times 4 is negative 4 m. And then finally we're down here to the last, 1 times 1, and we need to raise negative 1 to the fourth power, and that's going to make positive 1. So we got our 5 terms, and we did that by using Pascal's triangle. Okay, well, let's just take maybe just a quick look at the comparison. Maybe you wanted to use the binomial theorem. Well, the only difference is how do you get these coefficients. You don't have to make the triangle when you do the theorem, because you get those numbers 1, 4, 6, 4, 1 by doing combinations. You would start off with 4c0, m to the fourth, negative 1 to the 0. You notice the way we handle the terms in the parentheses is exactly the same. Okay, and then I'm going to do 4c1, m to the third, negative 1 to the first. No difference. If you did 4c0 in your calculator, you'd get 1. If you do 4c1 in your calculator, you get 4. So really, there's no difference in, the only difference really is how we come up with these numbers. 4c2, m squared, negative 1 squared. 4c3, m, negative 1 cubed. And then finally 4c4, m to the 0, which makes 1, and then negative 1 to the fourth. So it ends up being exactly like this. I just wanted to show you, just in case you wanted to use the theorem, this is how you would go about it. You would, if you chose to use the theorem, do not make the triangle, because it's not necessary. That's like doing double work. I mean, if you wanted to make it to check yourself, I guess that would be okay. But anyway, that is your final answer for number 4, and I hope that's enough to help you with either of the methods that you had to pick from. All right, number 5 is one of those where we had to identify the 7th term of an expansion. So that's utilizing the binomial theorem. Okay, just like this, this expansion has 5 terms. We're only wanting to, we want to identify only one of these terms in the expansion with this particular problem. If we were to expand this all the way out, it would have 9 terms. We just want to know what the 7th one is. So here's how we find it. We need a combination factor. This exponent will go to the left of c. And an easy way to remember the number to the right of c is just take 1 off of the term that you're asked to find. So 7 minus 1 is 6. If you wanted to count it out, that would be okay. The very first term of this expansion would have 8c0. Second term would be 8c1. Third term 8c2. You get the picture. If you wanted to do that all the way down until you got to the 7th term, you would see 8c6. But a quick and easy way is just to reduce whatever the problem is asking you to find, just subtract that by 1, and that number goes to the right of c. Okay, now just like we did before, we're going to take this first term in the parentheses. And an easy way to get this exponent, if you can remember this, is just subtract these two numbers. Or once again, if you just wanted to count at the beginning, the very first term, 2a would be to the 8th power. Then it would be to the 7th power. Then it would be to the 6th power, and so forth and so on until you get down to the 7th power. If you work your way down to that point, you will see that 2a would be to the 2nd power. And negative 2b, remember this exponent, the second exponent, and this second number to the right of C should always match. So you can kind of check yourself at this point. These two added together should always be the total of whatever this exponent is. This exponent and this number to the right of C should always match. And now you're ready to just grab your calculator, and you're going to do 8C6. So if you do 8 NCR6 in your calculator, you're going to get 28. This is 4a squared. Negative 2 to the 6th power is positive 64, b to the 6th. And now we just multiply all this together, and with your calculator, we get 7,168 a squared b6. And that's your answer for number 5. Number 6 is also using the binomial theorem to come up with a probability answer. Whenever there's a likelihood, two possibilities for likelihoods, in this case our two possibilities are balls or strikes, and we're told that they're equally likely to occur. So since there's an equal likelihood of either, I'm going to say 50% chance for strike, and then 50% chance for ball. Okay, we've taken care really of what this first phrase tells us. Now find the probability that 12 of her first 15 pitches are strikes. Well, I'm just going to go to the strike probability and raise it to the 12th power. And if 15 pitches are thrown and 12 of them are strikes, that means 3 of them have to be balls. Now we're about to multiply all this together with our calculator, but remember, this is one of the terms of a binomial theorem expansion, so we always need a combination factor. So just remember, the total number of whatever the activity is, in this case pitches, the total number of pitches goes on the left side. And then you can always remember this second part. We mentioned this earlier. It happens here, if you notice, this number to the right of C and this second exponent, which we would call the alternative to whatever the problem is asking for. The problem is asking for likelihood of strikes, so we came up with the alternative, which is throwing balls. Whatever this second exponent is, the alternative exponent, should match the second number after C. So if you set it up like that, you can now go to your calculator and let's type it in. You can do this all at once. I'm just going to break it up just so you can follow with me. If you do 15C3, just that part, you would get 455. Now we're going to multiply that times 0.5 raised to the 12th power. And then multiply that times 0.5 raised to the 3rd power. So just to kind of give you an idea, these are long decimals. I didn't think it's necessary to write them down, but in your calculator you're literally doing this. 15 NCR 3 times 0.5 raised to the 12th times 0.5 raised to the 3rd. And when you hit equals in your calculator, you're going to get a pretty long decimal, 0.01388,549. That's probably good enough. Now this is the decimal form, but I want your answer to be in percent form, rounded to the nearest hundredth. So the easy way to change decimal to percent is just to move the decimal 2 places to the right and round to the nearest hundredth. That means 2 decimal places. So my answer is 1.39%. Okay, I round this 8 up to 9 because the number to the right of it is bigger than 5. All right, so that's your answer for number 6. Moving right along. Number 7 is a long division problem. So the way we do long division is we divide first term into first term. So we need to divide 2x to the third by x, and we will get 2x squared. And now we're going to multiply 2x squared times each of these. 2x squared times x, and 2x squared times negative 2. And with long division, you always subtract. The 2x cubes will cancel, and this is negative 7 minus negative 4, which is another way of saying negative 7 plus 4. It's negative 3x squared, and then bring down the next term. Now we're dividing first term into first term again. So we're going to see how many times x divides into negative 3x squared. That's negative 3x times. Multiply negative 3x times both of these. Negative 3x squared. And then negative 3x times 2 is positive or plus 6x. Subtract. Okay, the x squares cancel. 7 minus 6 is 1x. And now bring down the next term, minus 2, and divide one more time. X goes into x, 1, positive 1. And now multiply 1 times each of these. And you'll see when we subtract that we're going to get a 0 remainder. So the answer for number 7 is 2x squared minus 3x plus 1. And you have another long division problem. So once again, divide first term into first term. How many times does x squared, if you divided x to the fourth by x squared, that's literally what you're doing, you should see that you'll get x squared. Remember that property? Division of like bases means you subtract the exponents. Okay, so x squared, we're just going to put it over its matching term, and now we're going to multiply x squared times all three of these. X squared times x squared, x squared times negative 5x, and x squared times 4. And subtract. The x to the fourths cancel. Negative 4 plus, because it's subtracting a negative, it's negative 4 plus 5 is 1x cubed. Negative 7 minus 4 is negative 11x squared. And then bring down the next term. Okay, repeat. X squared into x cubed. That goes x times. And now multiply x times each one of these. X times x squared. X times negative 5x. X times 4. Subtract. The cubes cancel. Negative 11 plus 5. Again, we have minus and negative. Negative 11 plus 5 is negative 6x squared. 34 minus 4 is 30x. And bring down the next term. And let's do it one more time. X squared, this time into negative 6x squared. Goes negative 6 times. And now multiply negative 6 times each one of these. Negative 6 times x squared. Negative 6 times negative 5x. And negative 6 times 4. And you can see when we subtract, once again, we get a 0 remainder, so this ends up being the final answer. That's number 8. Okay, now we come to some graphs. And we've talked about even functions. Remember, even functions should do the same thing on both sides. Here's what I mean by that. This is an example of an even function because the right side and the left side do the same thing. So this is actually a fourth degree, like x to the fourth, because there's 4 x-intercepts. But it's an even function. We know without even... well, one way we can tell is by looking at the ends. We call this end behavior. When the ends do the same thing, that means it's got to be an even function. And when they do something opposite, like this, right side goes up, left side goes down. Remember, odd means opposite. Okay, we talked about that before the last test. Well, applying that principle will help us in matching up these graphs with the appropriate equation. Something else that's always true, the number of x-intercepts is a clue. Okay, let's just take number 10 for example. We're already familiar with parabolas. Hopefully you're connecting parabolas with quadratics or squares. So we can go ahead and pair up number 10. It should be the only one of the group that is a quadratic. Okay, remember exponent 2 tells us we have the potential for 2 x-intercepts, and that's what this has. Okay, so number 10 has to, of course, be letter C. Let's go over to number 9. Do you notice how the right side and the left side do the same thing? So this has to be an even function. And with the ones that we have left, we've already used C. The only remaining function that's even is letter B. It's x to the 4th. So number 9 has to be B. Okay, remember even, and this has an even degree, the 4th power. Okay, now that takes us down to these final two, and I want to give you something that I mentioned in class earlier, but we haven't talked a lot about this. Another thing about end behavior that you can remember, if a function rises forever on the right, like this one, that means that its lead coefficient, the very first number in front of the very first variable, has to be positive. Okay, if the function goes down forever on the right, like this one, that means the lead coefficient has to be a negative number. Okay, so that kind of helps you out now with these final two. Another clue, if you think about it, is this. Notice where the x-intercepts are. Okay, of the two remaining functions, would you say that this is more closely a y-intercept of 8 than this one? Obviously, this has a y-intercept of 0. So you could have also paired number 11 with the d function, because this last number always indicates a y-intercept, and that looks about like it should be 8. But if you didn't think of that, you could always go with what I said earlier. This lead coefficient is negative, so you need to be choosing the function that goes down on the right. This lead coefficient is positive, so you're looking for the function that goes up forever on the right. All right, so to finalize this, we're going to say that number 12 goes with function A. Okay, it's cubic, odd degree, goes up forever on the right, down on the left, it does opposite, and the fact that it goes up forever means that its lead coefficient has to be a positive. And this goes down on the right, so its lead coefficient has to be negative. So I just want you to get familiar with degrees and behavior, and in general what the general shapes of functions are based on that information. That'll be very important as you go forward. Okay, I hope that helps for those matching problems. Alright, so let's do number 13. If we're given this function d of x, what do we get when we input 4a squared in for x? It's really what that means. So in place of these two x's, I'm going to input 4a squared. And simplify. Okay, you notice we just replaced the two x's with this. That's our given input. Okay, remember we need to do everything in my parentheses to the third power. So that's 4 to the third is 64. a squared to the third is a to the sixth. So that's 64a to the sixth, and this is like multiplying by -1. That's going to make it negative 64a to the sixth plus 4a squared plus 1. There are no like terms in this that can be combined, so that ends up being our final answer. I guess the thing to be careful about, the thing that I see a lot of people miss, is remember, this is a product. When you have a product being raised to a power, you raise both of the terms of the product, or ever how many there are. All of the numbers and variables that are being multiplied together need to be raised to the power. I see a lot of people that would say 4a to the sixth, but you got to remember you raise 4 and a squared to the power of 3. All right, so that's your answer for number 13. 14 and 15, and I believe 16, those are factoring problems. So 14, hopefully you're starting to recognize this situation. This is the difference between two perfect squares. I mean by that, these two terms have square roots. So anytime you see two terms that are being subtracted, the first thing that really should come to your mind is, do they have square roots, and is this really an example of the difference between two squares? A lot of times it will be. All right, so how do we factor the difference between two squares? We write the square roots. Really just write them twice in two groups. And in one of the groups you can make it plus, in the other group minus. And that's how you factor the difference between two squares. Well, we have that same situation here. These also have perfect square roots, and they're being subtracted. This cannot be factored. We can't factor the sum of two squares. But we do have a way of factoring the difference. Now, if there's a GCF, we could factor here, but there is no GCF. So we can factor this other difference between two squares as such. And that ends up being our answer. So be on the lookout. Understand how you factor the difference between two squares. It will come up on your test. All right, number 15. Remember, you always check for GCF first. So when we look for a GCF, we are looking for a number that will divide into 54 and 16, the largest number. And of course, that's going to be 2. And then we look for common variables, and each of these terms have y. So our GCF is going to be 2y. When we divide 2y into both of these, we get 27x cubed minus 8y cubed. Now looking in the parentheses, we have another special factoring case called the difference between two cubes. And we learned a few sections ago how to handle this factoring situation. So I'll bring down the 2y. The factoring of two cubes being subtracted, we write down the cube roots. Cube root of 27 is 3. Cube root of x cubed is x. Minus the cube root of 8 is 2. Cube root of y cubed is y. And now I'm going to make a trinomial factor based on these. So the first term of the trinomial will be 3x raised to the second power. It's 9x squared. Plus, now I'm going to multiply these together, 6xy plus, and now I square this last term, 4y squared. And that is the factoring for number 15. All right, another factoring problem. This is going to be our factoring by grouping. Anytime you're given 6 terms in a polynomial, like you are here, you're going to have to factor by grouping. And I went ahead, the problem's pretty much already laid out for you into the first 3 terms have something in common, and then the last 3 have something else in common. So I'm calling this red group. I'm going to factor out a 2y out of this red group. And when you factor out 2y, you get 3a plus 2b minus c. And then over in the blue group, if you notice, they all have z in common. So when you divide z into each one of these, 3a plus 2b minus c. So you know you've done the factoring correctly if your parentheses, the two parenthesis groups match each other. And so the answer will be these two terms that are not in parentheses. They'll go together to create one factor, and then this GCF, this matching parentheses, will be the other factor. And that's your answer for number 16. All right. Now we utilize factoring, and we're going to go a step further. So you notice the difference in this problem and the previous three. This one has equals 0. So now I've got more work to do. I've got to come up with the three numbers that we could plug in for x to make this equation equal 0. Now factoring is going to be involved, but I can't stop with factoring. If I do, I haven't solved anything. So please recognize when you have an equation, yes, you're going to do some factoring if it's possible, but then let your factoring lead you to the solution. Don't stop with the factoring. So once again, the first thing I want to do is factor out a GCF, which is x, and that gives me x squared plus 2x minus 35. Okay, now I'm looking inside here and seeing if I can factor more. And are there factors of negative 35 that add up to positive 2? And there are. So as two linear binomials, we could do positive 7 and negative 5. 7 minus 5 is positive 2, and 7 times negative 5 is negative 35. So now let each one of your factors, remember we're looking for three solutions, let each of these factors equal 0 and solve for x. If you let x plus 7 equal 0 and solve, you're going to get x is negative 7, and here you're going to get x is positive 5. So these are my three solutions for number 17. Okay, number 18. We can also factor. We learned the box method in dealing with quadratics, and I'll just show you that just like we did before when this was a quadratic equation. Now, one thing that's already determined for us, because of the way this trinomial is set up with minus in front of plus, remember that means when we factor, both of these have to be minus. And for that reason, I'm not going to worry about putting signs in this box because we already know what the signs are going to be. So when this was quadratic, remember we would do 8x squared and 3, put these two terms opposite each other, we'd multiply those together, and then the hard part of this for some people is finding the factors of 24x squared that add up to 10x. And hopefully you recognize that would be 6x and 4x. Okay, so then we would find our GCFs. So for these top two numbers, the GCF would be 2x, and this would be 1. Going this way, it would be 4x and 3. So when this was quadratic, we got our factoring of 4x minus 3, 2x minus 1. Well, the only thing we have to do to make this quartic factoring, which is fourth degree, is just let each of these x's become x squared. And now we've got the factoring for number 18. And now that we've got the factoring, we need to let each factor equal 0 so that we can solve. Now we're looking for 4 solutions. So each of your factors set equal to 0. Now let's solve for x. Add 3 to both sides. Divide by 4 on both sides. Now do the square root of both sides. Don't forget plus minus, and you do the square root of 3, which is not simplifiable. When you do the square root of 4, you can simplify that. That's just regular 2. So this represents 2 solutions because of plus minus. So I got half of my answers. All right, now let's work on the other factor. 2x squared equals 1. X squared equals a half. And now we're going to do the square root of both sides here. And you might be thinking, well, that's not the answer that I saw earlier, and you're right. I mean, it's along the way to getting to the answer, but my answer involved rationalizing the denominator. Since we have not covered that in this class, I'm not going to hold you to it on the test, but eventually we will get to this. I know you did it in Algebra 1. You may have forgotten. The square root of 1/2 in radical, if you just break up the two parts, numerator and denominator, it looks like this. And rationalizing the denominator means let's remove the radical from the denominator of the fraction by multiplying by that square root, top and bottom. And when we do, we get the square root of 2 over 2. So my answer showed a rationalized denominator if you saw the other answer on Moodle. But for purposes of the test, if you ran into this, I would accept this answer until we cover rationalizing, and then after that, I'll expect you to do that as well. All right, so that's your final answer for number 18. All right, one more. We're asked to solve, find the three solutions. This happens to be two perfect cube terms being subtracted, so that's why we learned how to factor these, so that we could solve these equations. So let's find out what the cube roots are. 2x minus 3. And now we're going to make a trinomial from these. Square the first term, that's 4x squared. Plus, multiply these together, that's 6x. Plus, square the last term. 3 squared is 9. Okay, make each of your factors equal to 0 and solve for x. So one of my solutions is 3/2. The other two will come out of this, and it doesn't factor, so I'm going to have to use the quadratic formula or completing the square. I'm going to do the formula opposite of b plus minus square root of b squared minus 4 times 4, which is 16 times 9, and that's 144, and all of that goes over 2 times 4, which is 8. Now let's work on that radical. 36 minus 144 is negative 108, and we can simplify the square root of negative 108 using I and two other factors, the square root of 36 times the square root of 3. Okay, and what's the square root of 36? That's 6. Remember, 36 times 3 is 108, and I takes care of the negative. So we're going to write this as 6i times the square root of 3 all over 8. And now each of these are divisible by 2, so we can reduce. So 2 into negative 6 is negative 3, and positive 3. And all of this is going to go over 4. So this represents two solutions because it's plus minus. So I circled all three of the solutions, 3/2, and then this is really two solutions. They are written together as plus minus. And that's your answer for number 19. So make sure you study hard on the difference between two squares, the difference between two cubes, the sum of two cubes, because those are very helpful factoring methods to help you solve equations. All right, so use synthetic substitution to find f of negative 2. We used to just directly substitute negative 2 in for x, but in Chapter 4 we learned how to use, it's really synthetic division. So here is finding f of negative 2. I put negative 2 in the house, and I'm going to do the synthetic division process. So bring down the 1, 1 times negative 2, add, 2 times negative 2, add, negative 7 times negative 2, add, and the answer, f of negative 2, is 16. Whatever the remainder is is like the output. If you input -2, the remainder is the same thing as the output of the function. And we'll just go ahead and do f of 4. So we'll put 4 in the house. Bring down the 1, multiply, add, multiply, add, multiply, 29 times 4, add. My answer here for f of 4 is 118. Okay, so remainder is the output from what we're used to doing with direct substitution. That takes care of number 20, the two-part answer. Okay, 21. If we know that x plus 5 is one of the factors, then what are the other two? There should be a total of 3. Well, we're going to use synthetic division. Remember, with synthetic division, we're dividing by some binomial x minus some number a or n. And we got to be careful because here, if we change this into subtraction, it would be like this. It'd be like x minus -5 to make x plus 5. So the bottom line is here we got to be careful. We're going to put -5 in the house. Okay? If you're given the binomial to divide by, you always need to do the opposite of the way this number looks to put in the house. That's crucial to get the answer right, that you remember that. Okay, 3, 2, 1, 0. Don't skip any terms. And so let's divide. Bring down the 3, multiply, add, multiply again, add. Okay, so we just proven that x plus 5 is a factor. Now we're going to take the remains of this. This is remainder, constant, linear, quadratic term. And we're going to factor it. Okay, so you could use the box method here. There's not a whole lot of options though. I don't think the box method is really worth it because to get 3x squared, you're going to have to do 3x and x. And we just need to put the factors of -2 in the other spots. To make 5x, that would have to be plus 2 here, because that's 6x, and then minus 1 here. So the answer, the other two factors, are 3x minus 1 and x plus 2. And that is your answer for number 21. It starts with synthetic division, and then you factor the resulting polynomial. All right. Okay, find all the zeros. This is going to utilize our most recent lesson information where we talked about the rational root theorem and we use synthetic division, the rational root test. Now this particular problem though, remember we talked about in class, there's a particular pattern that when it shows itself, it makes finding that zero a lot easier. The rational root theorem says that these are all possible rational roots, rational zeros. The factors of 6 over the factors of the very first number, which just 1. So these 8 numbers are all possibilities. But when you see this pattern where the coefficients 1 times 2 times 3 multiplied together equal the constant, then this is something that's always true. Your rational zero that you need to test will be the opposite of whatever is in front of x squared. So if you remember that, it'll save you a few minutes. Okay, so I'm only going to test -2. And just like with synthetic division, we write the coefficients and the constant across the top. So it's synthetic division looks a little different. 1 times -2 is -2, plus 2 is 0. 0 plus 3 is 3, and then -6 plus 6 is 0. Alright, so we found one of the 3 zeros. Let's find the other 2 using these numbers. They represent an equation. X squared plus 3 equals 0. So let's solve for x. X squared is -3. X is plus minus the square root of -3, which is I times the square root of 3. And we found our three zeros of this function, -2, and then positive I root 3 and negative I root 3. Okay, another problem like that. This time we're going to list out the possibilities for rational roots. Plus minus 1, plus minus 2, plus minus 4, plus minus 10, plus minus 25, 50, and 100. Got a lot more possibilities here than we had before. So I usually just start with 1, see what I get. And let's write the coefficients across the top. 1, -3, 21, -75, -100. Bring down the 1, multiply, that's 1, add, -2. -2 plus 21 is 19. 19 plus -75 is -56. And -56 plus -100, well, that's obviously not going to get it for us. So let's try 2. 1 times 2 is 2 plus -3, -1. -2 plus 21, again 19. 38 plus -75 is -37, and -74 plus -100. Well, do you notice as I choose bigger numbers, I just get more and more negative? So what I've just done is I've ruled out the larger positive numbers here, because I'm noticing a pattern. And remember, this is like an input and this is an output. It's like saying one of my points is 1, -156, and then I'm just going to do a little rough sketch. 1, -156 way down here, and 2, -174 is a little bit further, and that pattern is just going to keep going. I'm just going to keep getting further and further away from the x-axis, and I'm actually looking for numbers that are on the x-axis, remainder 0. So let's try some negatives, like -1. Alright, so -1 plus -3, -4. Positive 4 plus 21 is 25. -25 plus -75 is -100. And positive 100 plus -100, we found our first 0. Alright, so what remains is a cubic. X cubed minus 4x squared plus 25 minus 100 equals 0. Now, kind of interesting, I notice that the pattern has developed. 1 times -4 times 25 equals -100. So I don't have to go through all of that list again. I know that another rational root is going to be positive 4. 1, -4, 25, -100. Bring down the 1, 4 plus -4, 0 plus 25, 100 plus -100. Okay, 2 down, 2 to go. And now let's make an equation out of this. This is going to be quadratic. X squared plus 25 equals 0. X squared equals -25. So x equals plus minus the square root of -25, which is 5i. So we found all 4 zeros. -1, positive 4, positive 5i, and negative 5i. And that takes care of 23. Okay, 24. We're way back in chapter 1 review at this point. We're supposed to write an equation for a line. It passes through this point and it's perpendicular to this line. Well, the thing about perpendicular lines is they have opposite reciprocal slopes. So this line has a slope of 4. That's given. So this line has to have a slope of negative 1 over 4, opposite reciprocal. Okay, so let's take the point 10, 2 and plug in, and we'll use a slope of negative 1/4, and we'll solve for b. So y is 2, m is negative 1/4, x is 10, and let's find out what b is. This is going to be negative 10/4 if I multiply negative 1/4 times 10, so reduced, it's negative 5/2. And I'm just going to add 5/2 to both sides, so I'm going to treat this as 4/2. The number 2 is going to make it 4/2, and then when I add 5/2 to it, I get 9/2, or 4.5. And so my final answer in slope-intercept form is y equals negative 1/4 x plus 9 over 2. And that's the answer for number 24. Okay, 25. This is a linear system problem. There's two different options. We have this online store that we're getting digital photos printed. The online store is going to charge us a certain rate of 15 cents per photo, and then there's this flat fee of $2.70 for shipping. And then we have another way of paying the local store for photos. They just charge 25 cents each. So let's write an equation for each store. All right, the online store. I'm going to let C be cost, and I'm just going to let X be the number of prints, because we're charged by how many prints we have. All right, so the online store will cost 15 cents for every print. That's another way of saying 15 cents is the slope. And then there's this one-time fee of $2.70. Okay, so the cost really is going to depend. Remember, we call this it's the dependent variable, and this is independent. We input a number of prints in order to determine the output, which is cost. So the cost is really dependent upon how many prints we have. All right, so the local store, the cost there is just going to be 25 cents for every print. So that is your answer for letter A. These are the two equations that represent the cost of printing photos at each store. Well, for how many photos is the printing cost the same? Is C equal? For how many pictures? Well, if we want to know that, all we have to do is let these two equations equal each other. It's really substitution. I want to solve for the number of prints, which is what X represents. So I'm just going to let 0.25X represent, or fill in, substitute for C in this upper equation. It's just another way of doing substitution to solve a system. So 0.25X equals 0.15X plus 270. Solve for X. I subtracted 0.15X from both sides. And now divide by 0.10, and you get 27. So the answer to how many photos would result in both of these charging the same amount. They're going to charge you the same amount if you only want to print 27 photos. Okay? And then what is that cost? Well, for 27 prints, all we have to do is choose just either one of these. It really doesn't matter. And replace X with 27. The cost will be taking this bottom, the local store cost. They're going to be the same. Let's do 0.25 times 27. 0.25 times 27. And that is $6.75. $6.75. So it's a two-part answer. For how many photos is the printing cost the same? For 27 photos, cost is $6.75 for both stores. Okay. Well, when is it best? It's really asking for how many photos printed is it best to print online, and when is it best to use the local store? Well, let's just go one more. Let's just say we wanted to print 28. For the online store, if we wanted to print 28, let's just drop 28 in for X and see what we get for cost. We get $6.90. For the online store. For the local store, for 28 prints, 25 cents times 28, we get $7. So I know it's not much, but if you're going to print more than 27, then this shows that you should go with the online store. So we can word it this way. We've just kind of proven it. For more than 27 prints, he should use the online store. For less than 27, local store. 27 is really what we call the break-even point. So you can prove it just by going into either one of these store functions and replacing X with a number above 27 or a number below 27 and see what comes out. And that's your final answer for number 25. Okay, 26, 27, 28. This is a review of functions. And so our directions are state the domain and range. So let's start with number 26, the domain. That's another way of saying the x coordinates. That would be 5, 6, -2. The range, that's another way of saying the y coordinates. That would be 3, 1, and -8. It is a function. If you want to know whether or not it is a function, you cannot have any repeats in the domain. If you have repeat numbers in the domain in a mapping diagram or in a table of values, then you know that this cannot be a function. This is a function, and since there are no repeat y's, then it's both one-to-one and on-to. Okay, so that is your final answer for 26. There's a unique pairing. Every domain has a unique range and vice versa. Okay, so 27, let's state the domain. That's all the x coordinates, so -2, +1, and +4 down here at the bottom. The range, that's all the y coordinates, 3, 5, 2, and -1, if I'm reading those correctly. Okay, well, this is not a function. And there's really two reasons you could think of. I do see a repeat in the domain. The number 1 occurs in the domain, or the x values, 2 different times. So if you have any repeats in the domain, it cannot be a function. And another reason, if you didn't think about that, if you're just looking at a graph, we have this little tool called the vertical line test. And if I can draw a vertical line anywhere on this graph and touch 2 or more points with a single vertical line, then I've proven that this is not a function. So either way you want to look at it, the vertical line test or the repeat domain values, this is not a function. Okay, so let's go to number 28. Domain, -2, 1, 4, 8. Range, -4, -2, 6. Okay, this is a function because I don't have any repeat domains. It's on 2. It can't be 1-to-1 because in order to be 1-to-1, I can't have any repeats in the range. But all of my y values are accounted for, and I do have repeats. However, that's okay. I mean, it can still be a function, but it just can't be a 1-to-1 function. We're going to call this an on-2 function. Okay, so the big difference here is, well, you can't have any repeats in the domain to be a function, but if you have repeats in the range, it cannot be 1-to-1. It has to be considered on 2, as long as all of your range values are accounted for. All right, so that's 26 through 28. All right, we just have 2 more. So let's sketch this graph. This is a piecewise defined function. And so I've broken it up into colors. So let's draw this line segment x plus 2, y-intercept 2, slope of 1, but we're only drawing this line where x is less than 0. Okay, so actually for this y-intercept I'm going to make an open circle. And this whole line would go up 1, right 1, down 1, left 1, but since it says only show the line for x that is less than 0, we're not going to draw any part of this line to the right of this open circle. It's only going to go to the left. Okay, so here's my y-intercept and here's my slope of 1. And I'm going to connect those dots and just draw this. It's like a ray that extends only going left, never going right. Okay, and there's that's pretty close, I guess. There's the graph of the red piece. All right, now let's look at the blue piece. F of x is 2x plus 5, but only for this part. We're only going to show the line for x values between 0 and 2. So let's start with the y-intercept of 5 and a slope of 2, up 2, right 1, up 2, right 1. We could keep going in that way, but here is where x is 0. Okay, remember we're only going to draw this line to show x values on the line between 0 and 2. Well, here is where x is 0 on the line. Here is where x is 2 on the line. And so that's the only part of that line that we're going to draw. Okay, here's x is 0, here's x is 1, and x is 2. And that's the only part of the blue line that we're going to sketch. It's called a domain restriction. Okay. All right, that's the blue piece, and now let's do the green. Okay, let's draw the line -x plus 1, so it has a y-intercept of 1 and a slope of -1, so down 1, right 1, down 1, right 1, but we're only going to show this line for x values greater than 2. Well, here's where x is 2, so greater than 2 means I have to have an open circle. And then we're going to draw the line going to the right, since it's greater than, of that open circle. Okay. All right, so let me get my line draw. Okay, so there's the green section. All right, so now we're ready to state the domain and range. Well, for domain, you're thinking about all of the x coordinates that are utilized in when you put all of these pieces together. We are going forever and ever. If you combine all three pieces, we're going to have all real numbers. Thinking about the x-axis. Now let's think about the y-axis. Well, not all y values are used. There's a portion of y's right in here that are not used, and then all of the y's up this way are not used. So we're going to say the y values such that, let's take care of this blue piece first. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. We're using y values from positive 5 to positive 9. Okay, that takes care of the blue piece, and we'll say or equal to because they are solid. And then the rest of the y's start at positive 2 and go down forever, but we're not going to include positive 2. So we're going to say the rest of the y's will be all of the y's less than 2. And that takes care of the domain and range and the graph. Okay, so just a reminder of how to do piecewise defined functions. Our last problem, how do we change standard form quadratics into vertex form? Well, think about completing the square. So in the parentheses squared, I would have x plus and then half of 8. All right, I'm going to square this number. 4 squared is 16. I'm just going to go up to standard form and subtract 16. Put those two numbers together, I get negative 29. There is vertex form. It's as easy as that. Now, what's the vertex? The vertex will be negative 4. Remember, that's a translation. It's really 4 to the left and negative 29. And that's it. That's how you do vertex form. Think about completing the square here in the parentheses. That number squared will subtract off of standard form, combine those two numbers, and you'll get the y coordinate of the vertex. So, that was a lengthy video, but I hope seeing these problems helps you out, and study hard for this test.